Hey again everyone, and welcome to our introduction to capacitors. Capacitors are used in many applications. One of their most common applications are for filters or even for tuning in your radio stations, and all sorts of other applications we can use capacitors. That's why this is just an introduction. So I'll tell you a little bit about them, and then in later tutorials we'll get into all different sorts of capacitor circuits. Now, as you can see, I've got three different capacitors here, all made from different materials, and they give us different values of capacitance. Now, capacitors, just write this up, are actually measured in farads. So just like with resistors, we had let's say a 100 ohm resistor, capacitors were actually in farads. So this one here is a 22 microfarad capacitor. A 1 farad capacitor is a very, very large value of capacitance, and they usually use those in power supply circuits, or for those of you who have big stereos in your car, you might have a 1 farad capacitor connected across your power supply to actually supply power to the load in times of I don't know, lots of bass. Now, the circuit symbol for the capacitor is as basic as that there. We have two plates, so just made from some kind of metal, separated by what's known as a dielectric. Your dielectric can be anything from just plain air to paper to beeswax, and all sorts of other materials. Now, the factors that affect the value of capacitance is how big these plates are. If we make these plates larger, so we give it more surface area, then our capacitor value will increase. If we increase the distance between these plates, we actually decrease the capacitance. So if you think of magnets, for instance, if we had a north and south pole of a magnet, the further away these get, then the less we can feel that attractive force. So with a capacitor, if we move the plates further away, then the value of capacitance actually decreases. Now, we also have the dielectric constant, as it's called. That can also increase or decrease the capacitance. The dielectric constant basically is just the material it's made out of. So we've got the area of the plates, the distance between the plates, and then the dielectric constant that determines its value. Alright, so that's very good. So how does a capacitor work? Well, let's draw up our plates again. We have two plates. Now if I grab this capacitor here, and at the moment it's in its discharge state, it means that the difference between these two terminals, or these two plates, is actually zero. So what you'll find we'll have is, we'll have some electrons, and then we'll have our positive charges, or positive ions, which are actually holes. Actually, I should draw one more there, shouldn't I? So we have equal on either side, which means there's zero difference between them. So zero net charge. Now, with these positive ions, or these holes as we tend to call them, electrons can actually fill the space of the holes. So if we had free electrons, we could actually fill these holes with the electrons. If we got rid of some electrons, it would actually leave holes. So if we get something, for example, I might have all these here, and let's just pretend that these are electrons. If I was to take one away, I'm now left with a hole. That hole takes on a positive charge. So to get electrons to flow, they actually need to jump into the hole to actually get current to flow. And it looks like the hole moves in the other direction. So we're going to use that sort of basis to understand how this works. So, discharged, we've got 0 net charge. If we connect it to a battery, however, things can change. So we've got negative with respect to positive. So we've got the negative terminal to the bottom plate, positive to the top plate. Let's look at the negative first. Since this is an open circuit here, we don't actually get current flow through here. What we do get, however, though, is all these free electrons from the negative terminal of the battery or power supply, they will fill in these holes. So we'll get electrons coming from here, and an electron will jump in that hole, it'll jump in that hole, and that one, and that one. So now we're just going to be filled with electrons. If we look up the top, we've got the positive terminal connected to the top plate. The electrons in the top plate will actually be attracted to the positive potential. So if these electrons now leave here, we actually end up with holes, or positive charge. So the effect that connecting a battery or power supply to a capacitor is that we end up with a net negative charge on one end and a net positive on the other side. This capacitor will charge up to whatever voltage we have just applied to it, and it'll take a certain amount of time, which we'll go through in a minute. It'll take a certain amount of time to do that. Alright, so between the two we actually have a potential difference, or we have a charge. If I was to disconnect the power supply now, that charge will just remain on there. Because it's not a perfect world, after a certain period of time it will lose its charge, but let's just pretend that it's an ideal world. We disconnect that, this will stay charged. Alright, let's now look at a practical application by putting it into a circuit. So in this circuit we have two switches, we have a power supply, a capacitor, and a resistor. If I was to short circuit this switch, I will now get current flow in this part of the circuit. Actually, I shouldn't really say current flow like that. I will get electrons flowing to here and then building up on this plate, and electrons from this plate will move over to the positive terminal of the battery. So it doesn't actually flow through here, but we do get electrons flowing like that. So this capacitor will actually charge up to the full potential that we just applied. So the capacitor is now charged, and as before we'll have a net negative charge on the bottom and positive on top. If we then come and open circuit this, that will hold on to its charge. So leaving that open circuit now, I will now short circuit this one. So that's open, this is now short. I've got a full, let's call it 10 volts. I've got a full 10 volts difference between these two plates. So this now is acting as a battery for this circuit. So we've got negative down the top, negative down the bottom, positive up the top. We will get current flow from negative to positive through the resistor. Now, after a certain period of time, this capacitor will actually discharge. Just like a battery goes dead, the capacitor will lose its charge, will no longer get any current to flow in this circuit. Now let's have a look at how long it actually takes to charge and how long it takes to discharge. We have what's known as time constants. Now with our time constants, it actually takes 5 time constants for a capacitor to fully charge or to fully discharge. So we need to work out what one time constant equals. One time constant equals the resistance multiplied by the capacitance, and the answer is given in seconds. So let's have a circuit. Let's have a battery, a resistor, a capacitor. Let's make this 1 k ohm. Let's make this 10 microfarads. So 10 microfarads is this capacitor here would be about 10 microfarads. So one time constant is the resistance multiplied by the capacitance. I'll get my handy calculator and we'll punch it in. So one time constant equals 1k times 10 microfarads. And we're getting 10 times 10 to the negative 3, or 10 milliseconds. So if it takes 5 time constants to fully charge, and one time constant is 10 milliseconds, then it will charge in 5 times 10 milliseconds, don't even need the calculator for this one, is 50 milliseconds. So this circuit here, in order for this capacitor to charge up to whatever this potential is, it's going to take 50 milliseconds. If I was to increase the value of this resistor, it would actually take longer. The reason being, just got an email, the reason being is that we've got less current now. So if we increase the resistance, we've now got less current flow in the circuit. If there's less current flow in the circuit, then it's going to take longer for this guy to charge up. Or if this was a larger value of capacitance, then again it's going to take longer to charge up because it's physically a larger capacitor, or it's got a larger value of capacitance. Now I've just repeated the circuit here on its own page. But as the capacitor charges, something interesting happens with our circuit. So let's close this switch. We've now got a complete circuit. As soon as we close that, this capacitor was still discharged. Remember, it needs 5 time constants to charge up. It needs time. When we first close this is still discharged, which means it's got 0 potential difference. So 0 volts will be across that capacitor. If we've got 10 total, and this is grabbing 0 of that, then that leaves 10 for here. So how much current have we got? Well, it's voltage divided by resistance. There's 10 volts across the resistor when we first close this switch, and it's a 1 k ohm resistor. 10 volts, 1k is 10 milliamps. Now, as I was saying before, as time goes on, the capacitor charges. We've got negative here, positive here. The capacitor will actually be charging up the same, negative, positive. So let's say after a certain period of time, this now has a charge on it and a potential difference of 1 volt. If this now has 1 volt, we've got 10 total, that leaves 9 for the resistor. So how much current have we got now? Well, it'll be 9 milliamps. The capacitor charges even more, it goes to 2 volts. We've got 10 total, that's got 2, that leaves 8 for here. Our current is now 8 milliamps. So as the capacitor charges, we actually get less voltage dropped across the resistor. If there's less voltage there, then it means less current. So current actually decreases. So let's draw current up here. Current starts at maximum, and over time So this is time going across here. Over time, it just eventually decreases to nothing. So after a certain period of time, this capacitor here will get the full 10 volts, leaving 0 for the resistor. If there's 0 volts dropped across there, then you can't have any current whatsoever. So after 5 time constants, that's how long it takes for this to fully charge, which means that's how long it takes for current to go to nothing. After 5 time constants, this is now an open circuit. No current will flow in this circuit. If we look at voltage, however, so voltage across this capacitor, it starts out at 0. So we start down here. After a certain period of time, it'll charge up to the full 10 volts. So voltage does the opposite of current. So again, over time, voltage just keeps increasing, and eventually we get to it being fully charged. Now, after 1 time constant, and I'm going to approximate this to about here, after our first time constant, the voltage actually increases to about 63% of total. So if our total is 10 volts, after 1 time constant, which remember we worked it out before, it was 10 milliseconds. So after 10 milliseconds, the capacitor will actually charge to 63% of total, which would be 6.3 volts. Now after the second time constant, it will charge up a further 63% of what is remaining. So if there was 10 total, we already got to 6.3, then that leaves 3.7. So if we do 3.7 multiplied by 0.63, which is 63%, we get 2.3 volts. So we will now go up to 8.63 volts. So after our second time constant, we're about here, 8.6 volts. After the third time constant, we will go up by another 63% of what is remaining, which is going to be so about 1.4 volts, 63%. We go up by not even a volt, so 882 millivolts. So after the third time constant, we only go up to about there. And then fourth, we'll go up to about there. And finally at the fifth, we're not quite at 100%, but it's about 99%, so we say it's about 100%. So 5 time constants is how long it takes to get to our full charge. Each time constant we figured out was 10 milliseconds. So for this circuit here, it's going to take 50 milliseconds for this to charge to the power supply voltage. In this case it's 10 volts. Again, if we increase the resistor value, then we decrease the current. If there's less current, it's going to take longer to charge this guy up. If we make this a larger value of capacitance, again it's going to take longer because we've actually got more capacitance there, we've got more that we need to charge. In conclusion, capacitors store a charge. A capacitor will start to charge when we apply a potential difference between its two plates. The amount of time it takes to charge is determined by the value of resistance and capacitance in the charging circuit. After 5 time constants, we say the capacitor is fully charged. Also, once the capacitor is fully charged, we no longer get any current flow in the circuit because there is 0 volts dropped across the resistor. Therefore, we can actually use capacitors to block current in a DC circuit. You've been watching another Retro Brad video. Be sure to check out and subscribe to my channel for more electronic projects, hacks, how-to videos and tutorials. God bless.